No. Yeah, so lower the volume. Okay, so our speakers today are Shubhagata Bhaumik and Tanmaya Mishra from Florida Atlantic University. So they are part of the LIGO-Virgo-KAGRA collaboration, and they will tell us about detecting exceptional binary.
Thank you. Good morning, everyone. I hope people online can hear me. So we are final year graduate students from the University of Florida. I'm Tanmaya Mishra and she's Shubhagata Bhaumik. I'll be starting the talk and she will take over soon after. So today we'll be talking about expanding the gravitational wave frontier by detecting exceptional binary black hole mergers with a model independent search. So let us get into the basics. We are talking about gravitational waves. These are metric perturbations in space-time that were predicted by Einstein more than 100 years ago in his general theory of relativity. Similar to how we have electromagnetic radiation, when we have accelerating masses, they emit gravitational waves. But we need a time variation of the mass quadrupole moment for gravitational waves. And these waves are transverse and have spatial strain. So can we have gravitational wave emissions on Earth? Yes, we can. But the terrestrial sources produce gravitational waves that are too weak to be detected. So what sources are we talking about? The sources of gravitational waves that we can detect can be categorized into these four things. Broadly, they are of two types. One is long duration and the other is short duration. So for long duration, we have two types. The first one is, suppose you have some compact object which is rotating and it does not have spherical symmetry. Then we can have non-zero time variation of the quadrupole moment. For example, a rotating neutron star with surface imperfections can give rise to continuous gravitational waves. The other long duration source is stochastic gravitational waves that were emitted in the early universe. It's similar to having a cosmic microwave background. We can expect a cosmic gravitational wave background. Then we have the short duration sources, which is what we work on. And these are primarily of two types. The first one is called compact binary coalescence, where we have two compact celestial objects forming a binary and merging. These can be two black holes in an orbit, a binary neutron star, or a combination of neutron star and black hole. Let's call them as CBC from now on. And then the last type is burst sources. The best example for that is a core collapse supernova. Now, another thing we can do is we can say that these sources can be modeled. That is, we can have some waveform simulations made for these models. Whereas for these sources, they're categorized as unmodeled. It is hard to give an analytical waveform. Now, what have we detected so far? So we have detected around 90 CBC signals in the first 3 observing runs of LIGO-Virgo-KAGRA. And these are made by ground-based detectors. So now let's see how we are able to detect such events. So once we have, say, a compact binary black hole merger, the signal will pass through Earth, and we can capture it by using laser-based interferometry. So this is a Michelson-based interferometer where we have 2 perpendicular arms. They're set up such that the laser travels equal paths, such that there is no output in the photodetector. Now, if a gravitational wave passes through this detector, then what we have is a change in the path length, delta L, and we can detect these in the photodetector output. So an example would be the first signal that we ever detected here. So what we are measuring here is delta L over L, the strain, and the strain signal from a gravitational wave merger looks like this. So here we can see 3 distinct phases of the binary evolution. So the first one is in spiral, where it is the binary is falling towards each other, and we have the merger and ring down. So merger is when the coalescence. So the amplitude and the frequency of this waveform monotonically increases till the merger. And then there is a small ring down of the remnant black hole. But the thing to note here is that the sensitivity that we require is of the order 10 to the minus 21. So to detect such signals, we need very sensitive detectors with the noise spectral density looking something like this. So it has to go very high sensitivity. So these detectors are called, one of these detectors are called LIGO detectors, which is Laser Interferometer Gravitational Wave Observatory. There are two such detectors, one in Hanford and the other in Livingston. And they have a 4-kilometer long arm length that allows us to attain sensitivity of 10 to the minus 23. In this plot here, we show the sensitivity for the Livingston detector in the O3 run, or the third observing run. And we show examples of gravitational waves that we have detected in the Fourier domain. So here we can see the in-spiral merger and ring down for a 60 total solar mass event, which was the first event, GW150914. Now, as we increase the total mass of the binary, the merger frequency, which is inversely proportional to the total mass, decreases. So we see that the frequency that is seen in the detector is decreasing as we increase the mass. And the last thing to note here is that if we increase the mass to say 150 solar masses, then the signal that is detected by the LIGO detector in the observable band is getting lower. So the sensitive frequency band for LIGO is somewhere around 10 to 1000 hertz. And so far, this LIGO-Virgo-KAGRA collaboration has detected 90 such binary black hole events. So now let's look at what the current status of the gravitational wave network is. So apart from the two LIGO detectors, we also have a Virgo detector, which is 3-kilometer long arm length. And we have a prototype GO600 in Germany. Then we have an underground detector in Japan called KAGRA. And very recently, LIGO India has joined this collaboration. And the detector construction has been sanctioned, and the land has been acquired in Aund, and construction has already begun. And this is expected to join the observation in the later half of this decade. Now, how does this affect our sensitivity? So this is the sensitivity we had in the first 3 observing runs. In the 4th observing run, which is currently ongoing, we have around 150 megaparsec sensitivity to a binary neutron star merger. For the LIGO detectors, for Virgo, it is around 50, and KAGRA had some problems, but it is expected to join again at the end of O4, around at the end of 2025. So, and in O5, we expect to improve the sensitivity even more to 240 megaparsecs. But this is not all. We have other detectors joining this fray, such as LIGO India. When it is operational, it is expected to again have similar sensitivity as O5. But this is not all. We also have Einstein Telescope and Cosmic Explorer ground-based detectors, which are currently under planning, and they will be significant once they are built. Now, what have we seen so far? So let me just show this image, which shows all the observations till the end of 3rd observing run of LIGO-Virgo-KAGRA. And what we see here is the black holes that are observed by EM electromagnetic observations. And we can see that above, say, 2025 solar masses, we could not have detections from the EM counterparts. But since the beginning of LIGO-Virgo-KAGRA, we have now populated this mass spectrum of black holes. And the other thing I would like to bring the attention is that above 100 solar masses, we do not have many observations. And this brings us to the next topic, which is intermediate mass black holes. So these black holes are in the mass range 100 solar masses to 10 to the 5 solar masses. And they kind of provide the missing link between stellar mass black hole and supermassive black holes. And so far, we have had various IMBH candidates from EM observations, but nothing has been conclusive until in the third observing run of LIGO-Virgo-KAGRA, we detected the most massive black hole. It's called the GW 1905-21 event, which happened in 19th May. Sorry, 21st May. Yeah. And this provided the first conclusive evidence of IMBH. And this has a total mass of 142 solar masses, falling directly in the IMBH mass range. And this was not all. The heavy black hole in the binary had a component mass of 85 solar masses. And this is very interesting because this sheds light into another interesting topic called the pair instability mass gap. So we know that in stellar evolution, for lighter stars, they will either end up as a neutron star or black hole after supernova. But if the helium core mass is large enough, then we can have conditions that are suitable for pair production. And this positron-electron pair production at the core reduces the radiation pressure, which causes the star to implode on itself. And if the core starts imploding, depending on the mass of the core, three things can happen. The first one is if the helium core mass is between 32 and 64 solar masses, then there will be pair production, and there will be something called as a pulsational pair instability, where there will be small supernovas which will be occurring regularly at a certain time interval that will help the star reduce some of the mass, get rid of the mass, and then at the end it can form a remnant black hole mass less than 64 solar masses. Now, if the helium core is sufficiently large, greater than 135 solar masses, then it will directly collapse to form an intermediate mass black hole. But if it is in the range 64 to 135, then the pair production is sufficient such that there is a single pair instability supernova, which leaves no compact remnant behind. So what we expect is a gap in the detection of black holes from 64 solar in this mass range, 64 to 135 solar masses. We do not expect to see any black holes. And here we can see the LIGO-Virgo-KAGRA observations, where we have highlighted the GW 1905-21 event. What we can see is that the total mass, it lies in the IMBH space, but also the interesting thing is that the primary component or the heavier black hole in the binary falls directly in this PISN mass gap. And this raises very important questions on the possible formation mechanisms of this black hole. So I'll discuss some formation channels that we can think of. One is hierarchical mergers. So in this, we expect, let's call them first generation black holes that are stellar mass black holes to merge and give us heavier second generation black holes. Now, if the heavier second generation black hole is able to find another first generation black hole and form a binary, then it could provide suitable conditions to get an 85 solar mass black hole. This is one way that in which we can explain the formation channel for this event, but we need a very dense cluster for this to happen, because otherwise, after the merger, the black hole will be shot out of the environment. The other interesting mechanism is in an active galactic nucleus. So when a supermassive black hole is accreting, it can provide a very dense environment and trap tens of thousands of black holes in its accretion disk. And in this disk, we can have a hierarchical merger system. And this is some sort of an AGN collider, which is colliding black holes. And it can give us heavier black holes. Now, the third mechanism is a stellar merger scenario. For this, we need a giant star with a helium core. And if it can merge with a main sequence star, then we can have an oversized hydrogen envelope with a helium core. And in such conditions, it can directly form a black hole in the PISN mass gap. So these are some of the formation channels. Now, I'd like to give the mic to Shubhagata to explain how to distinguish between formation channels.
I hope everyone on Zoom is able to hear me. So I'm going to talk about how, so Tanmaya talked about the various formation channels that can lead to binary black holes. So I will talk more about how we can distinguish these different formation mechanisms. Now comes the role of eccentricity in this. So when you have a binary black hole system, it can either be circular orbit or it can be eccentric orbit, and this can tell us a lot about where it came from. So in general, we talk about isolated field binaries, which are binary black holes in isolation from any other astrophysical objects. What happens in these isolated field binaries is that you have two stars that evolve together and form two black holes. And this is a long process because each of the stars goes through its stellar evolution, undergoes supernova, and eventually forms a binary black hole system. And because these are long-lived binaries, what happens is that through gravitational wave emission, any eccentricity that could have existed in this binary orbit is emitted away due to gravitational wave radiation. So the main point to take away here is that long-lived binaries circularize due to gravitational wave emission. Therefore, by the time LIGO can detect them, they basically have negligible to zero eccentricity. So if you have a binary from an isolated channel, you can basically expect that these are quasi-circular orbit binaries. Now, in the other scenario, if you have binary black holes that are dynamically formed, which is when you have black holes that encounter each other by chance in dense environments, they can actually retain eccentricity that LIGO can detect. This is because they can meet each other at very small separations, and by the time they meet each other and the binary orbit hardens, they are already detectable by LIGO, and therefore, if the orbit is eccentric, LIGO can detect them. Another mechanism by which you can have eccentricity in the binary's orbit is when you have a binary system that is perturbed by a distant object. For example, you can think of a binary black hole system that is in the vicinity of a supermassive black hole. So this perturbation from this distant object can cause the binary's orbit to be eccentric. So LIGO can detect them with eccentricity if we have such a scenario. In fact, if the perturbations from this third object is high enough, the eccentricity can be driven to very high values, which can lead to, so if you think of very high eccentric binaries, it's like very elliptical orbits. So basically, they can come to very small separations, which lead to gravitational wave bursts, which cause the binary to merge even faster. And lastly, you can have an eccentric binary when you have mergers within the AGN disk that Tanmaya talked about. In this, studies have shown that binary single systems are very common. So you have a binary orbit which has a third black hole sort of orbiting this system. And this can lead to eccentric mergers because, again, perturbations from the third object. And some studies which I have highlighted here show that about 40% of mergers from this scenario can have eccentricity that LIGO can detect. So the main takeaway from here is that if you have eccentricity, the binary was formed dynamically. And if you don't have eccentricity, you could say that the binary was formed in an isolated environment. But in order to look for eccentric signals, the first thing we need to understand is how they are different from quasi-circular orbit binaries. So here on the top panel, I have an eccentricity 0 or a circular orbit binary. And all these panels show gravitational waveforms for the same mass. So total mass of 80 solar mass, and the two masses are equal. So what I have done here is I have increased the eccentricity of the orbit gradually to show you how exactly the signal morphology changes as you increase eccentricity. So the first plot here is your typical chirp signal that you see for gravitational waves, where the amplitude as well as frequency are monotonically increasing in time. Now I slowly increase the eccentricity to 0.2. And what you see here is that the amplitude is no longer monotonically increasing. You see these oscillations in amplitude. And as you increase the eccentricity, these oscillations become even more dramatic. So the signal morphology dramatically changes as you increase the eccentricity. And another important thing to note is that something that was 20 seconds long for a circular system, as I increase the eccentricity to 0.7, this signal is not even a second long. So the duration of the signal becomes shorter and shorter as you increase the eccentricity of the orbit. So basically, eccentric waveforms are quite different actually in morphology from quasi-circular binaries. And therefore, we need to make sure that our searches can actually look for these signals and they don't reject them as noise. So that brings me to talk about searches for gravitational waves. So, oh, yeah.
In case of these complicated mergers with large eccentricity, we also have a more complicated dependence on the direction of view, so to say.
So the direction of view is usually, so the orbit, the plane of the orbit, it usually is along the z-axis. But what happens in a scenario like this, when you have the quasi-Lidov mechanism, is that the plane of the orbit also oscillates, in which case the direction of view sort of oscillates and it can cause even more, these dramatic oscillations here. Here I have the inclination fixed. These are just changes with eccentricity, but you rightly point out that if you have something like this, things could become even more complicated with the morphology of the signal. So coming to searches for gravitational waves, I'm first going to give you a broad overview of the searches that LVK or LIGO-Virgo-KAGRA employs to look for any general gravitational waves. So there are mainly two types of searches, modeled and unmodeled. As the name suggests, modeled searches look for sources that are already well modeled, that Tanmaya talked about. And in order to perform these searches, you need accurate template banks. So these template banks span like mass, spin, space, and you basically have these template banks that are accurate waveforms that represent each point in mass and spin space. And what you do is you pick up each template from this template bank and cross-correlate it with data. And if you have a peak in the cross correlation, which is greater than some predefined value, let's say 95% match between the template and the data, then you can claim that there is a gravitational wave hidden within the detector noise. So these are model searches, and as you probably got from this, you need very accurate templates. If the templates are not accurate, this cross correlation can actually not be efficient. Some examples of such searches are PyCBC and GST-LAL. But in our group at University of Florida, we specialize in unmodeled searches, which basically look for sources which are not accurately modeled yet. But we don't want to miss out on these searches just because they are not modeled. They could still be very interesting to us. So they look for sources with making minimal assumptions about the signal morphology. And because of this, they can detect unmodeled sources like gravitational waves from core collapse supernova or poorly modeled CBC sources. For example, eccentric binaries are still not as well modeled as circular orbit binaries. So for this, unmodeled searches are very suitable because, as I said, the cross correlation is not good enough if you use poorly modeled CBC signals. So I'm going to talk about one such search in more detail called the Coherent WaveBurst. This Coherent WaveBurst algorithm was actually invented by one of our professors who is at University of Florida, Sergei Klimenko. So the problem, even though there are a lot of advantages with detecting eccentric binaries, there are also a lot of challenges that come with this. And one main challenge is that currently template bank searches cannot be employed to look for these signals. This is because there is a lack of accurate eccentric templates, as I mentioned. And one might ask the question that, okay, what if you just take the circular binary template bank and use it to look for eccentric signals? But this will not be efficient because many studies have shown that loss in the match between the waveforms is very significant for eccentricities greater than 0.1. So what this means is that these modeled searches can only look for eccentric binaries with eccentricities up to 0.1. Beyond that, the cross correlation is not good enough. Another problem is that, as I mentioned, eccentricity is lost as gravitational waves are radiated. And therefore, unlike masses of the black holes, eccentricity is not constant throughout the evolution. It's a time-dependent quantity. And therefore, it must be defined at a reference frequency, which makes analysis a little complicated. Another problem is that eccentricity is sort of a weird concept for binary black hole system, because eccentricity is a property of a closed orbit, but these are not closed orbits. So the definition itself has not been standardized yet and can vary between different waveform models, which makes it hard to compare results. Even though there have been these challenges, many studies were carried out to look for any signatures of eccentricity that already exist in the detected set of binary black holes. And I will highlight two very nice studies which showed that one of them showed that there are at least 4 events within GWTC3, which is the catalog of binary black holes detected in the first 3 observing runs. So they showed that there are at least 4 events that show some minimal signs of eccentricity, about 0.1 to 0.2. And there's this other nice result that I want to highlight, which is that the GW190521, which is super interesting because, as Tanmaya pointed out, one of the masses lies right in between the pair instability mass gap. So to understand this event better, we try to look for eccentricity in the orbit. And highly accurate numerical relativity waveforms were generated just to study this event. And what the authors saw was that this event was most consistent with an eccentric orbit of 0.7. So this is actually one of the first detections that shows very high proof of eccentricity. But one caveat that I would like to point out is that this, because of being so heavy, this signal was very short. And therefore, a lot of studies also showed that it could be a high spinning system and not eccentric. So because it was so short, it was hard to look for very conclusive proof of eccentricity. So in order to look for conclusive events that are eccentric and not quasi-circular, yeah. So this is actually not the search. The search already provided this catalog of binaries. Then they use parameter estimation to estimate the parameters of all these binary black holes. So for this particular event, the search already resulted in some signal, and they estimated the parameters of this signal. And for that, they used very accurate waveforms. Yeah, they used numerical relativity waveforms, which are the most accurate that you can get. And usually, you don't use them for parameter estimation because it's very expensive to generate these. But because these were short signals, we were able to generate numerical relativity waveforms. But no, they are not. Because for low mass, it's like it'll take months to years to generate these waveforms. But because this was like less than a second duration of signal, we were able to make NR waveforms for this parameter space. Yeah, so to look for these signals, we employ the model independent search because there is a lack of accurate models to describe these systems. So to start with, I'm going to give you an overview of the coherent WaveBurst algorithm, which is what we use to look for these sources. So it is a model agnostic search algorithm. And what CWB does is looks for coherent energy that is present across the network of detectors in the time frequency domain. And if it finds any data segments that pass this criteria, what coherent WaveBurst does is that it extracts the properties of these signals. For example, the duration of the signal, the energy contained in the signal, etc. And using these properties, we are able to categorize these signals as either true events or noise. And this is very important because I show you one plot here. This is a simulated signal for a binary black hole of total mass 200 solar mass, and this is a glitch. So what you can see in this plot is that glitches are basically noise sources in the detector. you can see that the noise signals can actually mimic the true signals very, very well. So you need to be able to distinguish between the two, and the properties that coherent waveburst extracts from the signal helps us to distinguish between the two even better. So here I can show you one example. So here is one of the properties that CWB extracts. And these are noise events, the orange curve, and the blue is the simulated signals. And you can see that there is a tail in the noise curve, which makes some region of space of overlap between the true events and noise signals. So in the older version of CWB, what we used to do is place these thresholds to say that if the signal has statistic greater than 4, for example, it's most likely a signal. And if it has statistic less than 4, then it is most likely noise. And this is just one example. It used to be a multidimensional space of like 20 summary statistics. And for each statistic, we used to place a cut. And if a signal passes all thresholds, then we can confidently claim that this is a true detection. So for the eBBH search, we saw that some of these thresholds were removing high eccentricity signals, because as I showed you, the high eccentricity signals are very short duration. So they were removed as possible sources of noise. But what we did was tune them to make them more efficient to not removing very eccentric signals while still removing noise. So that brings me to the O3 eBBH search, where eBBH stands for eccentric binary black hole. So using this tuned or optimized CWB search, we carried out a specialized search to look for eBBH signals in the O3 observing run of LIGO-Virgo-KAGRA. So the goals were as follows: optimize CWB for eBBH signals, carry out search in O3 data, and if we got any interesting events, we wanted to follow up to see if it was truly eccentric or if it was a noise source or if it was something else, and make astrophysical interpretations of these search results. So this was a collaboration-wide effort, and the paper was recently published in AppJ. So we performed this search on O3 data, and we got one event that was not seen by circular-based searches or model searches. But as you guys can probably see, the energy is mostly coming from one detector, the Livingston detector. So we wanted to see if this was any source of noise that maybe existed in the Livingston detector at that time. But we were not able to conclusively find any source of noise. This event also had an IFAR or inverse false alarm rate of about 1 year, which means that the false alarm rate was about 1 per year. So it was not a super significant detection. So for any astrophysical interpretations, we just assumed that we did not make any eccentric gravitational wave detections, but we were actually not able to conclusively prove if this was actually noise or an eBBH signal. So even though we have non-detection, this non-detection actually helps us make astrophysical interpretations, because it can help us constrain how often these systems actually form. Because if we are not able to see them and we know how sensitive we are, we can basically place an upper limit on how often these systems actually form. So we did that, and to do that, we used highly accurate NR simulations. And because these are expensive to compute, we were only able to span the high mass space. So we saw how sensitive LIGO-Virgo-KAGRA detectors were to eccentric signals, and how this sensitivity varies with eccentricity and mass. So one really nice result that we saw was that with eccentricity, our sensitivity doesn't change, at least up to an eccentricity of 0.3, which is great, because this means that CWB, if there is an eccentric signal, CWB is will be equally equipped to detect this signal as it is for circular binaries. And using this, we were able to place constraints on merger rates. And we saw that the constraints that we placed agreed very well with astrophysical predictions by astrophysical modelers. So now Tanmaya is going to talk about how we upgraded CWB to the next level to make it even better.
So going to the next slide. So in preparation for the fourth observing run, there were two major upgrades done to CWB. The first one is related to how CWB finds these events in the time frequency domain. So a new time frequency transform called WaveScan was introduced by Sergey in 2022. And the good part about this is that it can provide us very high resolution time frequency maps, where it is also able to suppress the temporal and spectral leakage. And this is important because now when we extract the source properties of the signal, we can get even more accurate numbers for that. And the other upgrade was in this was that in addition to the excess power that Shubhagata talked about, we now also use cross power statistics, which makes the identification of transients even better. Now, the second major upgrade to CWB was in the post-production part, or where we are differentiating between a true signal and noise. And instead of doing it by putting thresholds on the summary statistics, we now use machine learning method. So what we do is we take a selected set of summary statistics and feed it to a classifier algorithm called XGBoost, where basically it creates an ensemble of decision trees, each based on the previous decision tree, and gives us an output. Now this output is set up such that it goes from 0 to 1. It's called WXGB. And if it is 0, it means that it is most likely a noise event. And if it is 1, then it is a true gravitational wave signal. And the way we use it is we don't directly depend on machine learning, but what we do is we take the coherent SNR of CWB and we use this machine learning output as a penalty factor to it. So what we are doing is we are effectively reducing the coherent SNR for noise events. This can be seen in this histograms here. So on the left, the gray curve is for the noise events, and the red and magenta curves are for different types of CBC simulations. So once we apply XGB and re-rank these events, we can see that the background or the noise events are very well suppressed and constrained. So we do not have a high tail that goes over to the simulation. At the same time, we are also able to recover most of the simulation events. And in this search, we now are able to look for both stellar mass and intermediate mass binary black holes using the same setup. Now let us look at some search results on the third observing run data. So in this left plot, we show the ROC for the sensitive hypervolume for CBC BBH merger signals. And in this black curve is the old CWB with the thresholds. And the red curve is with the upgraded CWB with machine learning. And say at a false alarm rate of 1 per year, we have around 40% improvement in the sensitivity. Now we also show the detections in O3 in this plot here, where the detections are shown cumulatively and the inverse false alarm rate of the significance is plotted here. And the light blue and dark blue are for the old coherent WaveBurst searches. The dark green curve is for the new updated CWB. And now if we remove the known candidates from O3 that were detected by the template-based searches, then we get this red curve here. So what we see is that we have new events that were not detected by the template-based searches in this updated CWB search. So I would also like to point out how it performs for high mass events. So again, taking a look at GW 190521, now the wave scans are much clearer, and the final event that is extracted is looks like this, the cross power distribution, and an inverse transform gives us the time domain signal. And you can see from the reconstructed signal that this is very much looks like a glitch that Shubhagata talked about. But with this updated search, we are able to detect it with the highest significance as compared to any other template-based searches. Now, the fourth observing run is ongoing, and in the first half, which was from May 2023 to Jan 2024, this updated search was used in the low latency searches, and it was able to detect 70% of all the significant candidates that were sent out. And currently, we are doing the offline analysis for the O4A events, and O4B run has already started in May 2024 of this year. So to summarize, we would model independent searches like Coherent WaveBurst are very crucial in detecting any uncommon sources like eBBH mergers or IMBH mergers. Recently, it was optimized for the eBBH search in O3, which resulted in a collaboration-wide publication. And for O4, we have now upgraded CWB with WaveScan and machine learning, which improves our sensitivity by around 40%. And in O4 run, we already have promising results. Like we have detected 70% of all the public candidates that were sent out. And we are expecting to see more unexpected gravitational waves before the end of this run, with maybe many exciting sources like hyperbolic encounters or unequal mass ratio mergers. Thank you. We'll be happy to take any questions.
So how many parameters do you describe this type of mergers with eccentricity? Is it just one additional parameter, or is there more?
Do you want to say?
So that's a very good question. It's actually not enough to just have one additional parameter, but we actually require two additional parameters. So one is the eccentricity of the orbit, and one is where you are on the orbit. And that's usually called the mean anomaly. So to make sure that there are no degenerate cases, we actually need these two, because frequency is not monotonically increasing. We have these oscillations in frequency. So an eccentricity could actually, just saying eccentricity and flow could actually mean two different things. So you have to specify where you are on the orbit.
And maybe just to add, so talking from the search perspective, what we could do is maybe identify some signature here that relates only to eccentricity. And if we can get that, we can put it in our machine learning algorithm, and then we can have a eBBH search. Yeah.
Can you be used for like transient sources or like and paste it into one model like to that burst?
Yeah, I think right now we are limited by person power, so we only have a dedicated binary black hole search from Coherent WaveBurst. We also have a generic search which searches for all kinds of burst events, but we are not yet doing long duration search, but it can be done by correctly setting up the CWB. Yeah.
Asked already a couple of questions, but I've got one more. So if you when analyzing an event like that, when you allow for non-zero eccentricity, how much does it bias other parameters like the masses or the mass ratio?
It actually biases. So if I go back to this slide, if you estimate the parameters using a circular template, for example, high eccentricity could actually mimic a high mass event. So that is a big problem right now, which is why in order to make unbiased estimation of the parameters, you have to include eccentricity, because there are various ways in which the other parameters could be biased, and the two main ones are the mass as well as the spin. So there could be correlations between how high spin systems and high eccentric systems actually mimic each other.
Maybe we will explain this.